today is covered, like as usual, 2 different chapters. And the chapter that I would like to cover right away is one related to what we have covered so far. And the last accident that we dealt with was the wind scale accident, which is also named Sellafield. They changed the name of the location from Windscale to Sellafield. And remember, the Sellafield reactors were graphite moderated reactors. And one cause of the accident is basically, first, it was a design flaw. Second, human error in the process of annealing the graphite because of the Wigner energy, which comes from the radiation damage caused in the graphite from neutrons. And it ended up with a nasty fire, as you remember. Of course, the graphite is carbon. So if you heat up carbon to a very high temperature, it starts interacting, basically burning, oxidizing, and you get a fire. And the fascinating thing is that that also happened in the case of, guess what, the Chernobyl accident. So let us see. And Chernobyl, in fact, was a graphite moderated reactor. So we'll spend our day today with the Chernobyl accident. It immediately put me here on parts of the chapter that shows us that at Chernobyl, even though we had a fire like the Sellafield or the Windscale accident, but we definitely have had probably also a steam explosion. And that is a major design flaw that was in the Chernobyl type of a reactor, the RBMK 1000. And you see in that picture what was the situation at the end of the accident. The whole core region, which was having a graphite as a moderator, has disappeared. It caught fire. It ended up with debris at the bottom of where the core was. But look here, the upper biological shield, a slab that is 800 tons, metric tons, 6,000 kilograms in weight, has been thrown up and then back down again. And the content of the core also has been thrown up, right? So you see it here, that's a pile of material thrown. Well, also they tried to distinguish the fire by materials from helicopters, but part of the core was thrown up. Let's see here in that diagram, another flaw in the design is that here at the bottom, as we'll see as we proceed further, they have basically water as a coolant. They called it the condenser in other diagrams, and it is not shown in the diagram, but the suspicion is that the core melted through the bottom and interacted with the water, and that is what caused that steam explosion that threw up the lid up in the air. So let us see what went wrong with the Chernobyl accident. It's one of the major accidents that happened in the nuclear industry in general. And it has been recent. It happened in 1986. And it happened in 1 out of 4 units that were operated at the site called Chernobyl. And only one of the units caught fire, unit number 4. And in fact, the other 3 units continued operation for quite a while. And this is a picture of the damage that occurred to unit number 4. You'll find here total destruction. The core caught fire, and not only caught fire, but it exploded, literally exploded. You could see here parts of the core have been ejected into the neighboring here buildings, and it was on fire, so they burned the roof of the building. Right now, the Chernobyl reactor that has been damaged has been enclosed in a silo made out of concrete and waiting for the radioactivity to come down. And the radioactivity goes down as a function of time. And then later on, it will have to be disposed of into the ground, basically. What is RBMK? RBMK is an acronym stand for, in Russian, Reaktory Bolshoi Moshnosky Kalalini, I think, you can see the etymology of calorie or heat. That translates into high power pressure tube reactor. So these were reactors that were cooled with light water, and light water was allowed to boil. And as it was allowed to boil, steam was produced, but the moderation was not like light water reactors from water or from heavy water. The moderation of the energy of the neutrons to turn them into thermal neutrons was made out of the graphite. So there is a distinction in two functions in the core. The coolant as acts, in fact, as an absorber for the neutrons. So it acts as a control rod. And if you boil that water that is acting like a control rod or a poison, you lose. It is equivalent really to withdrawing the control rods. And in that case, we call that type of reactor a reactor that has a positive power coefficient of reactivity. So let me expand on that positive power coefficient of reactivity. If you get yourself into a course where you study control theory, you'll find that we like to display any control system, but say, let's call it in the with a box here. The box is giving us some output. Let's call it here output here. And you have control rods controlling the reactor, but then you have different physical phenomena, including the control rods that can be controlled. So we take a feedback from the output into basically control function in the Laplace domain, and we feed it back into the system. That feedback is compared with the input to generate really the control signals to the reactor itself. In essence, any stable type of configuration for any control system has that negative sign here, meaning that the output depresses the input. And in that case, if you have a perturbation that happens to the system, let me show the perturbation as a perturbation like this, you'll find that it decreases exponentially. A system of that nature is called the negative feedback effect. If you have that positive, you'll find that any perturbation of the system, say a small perturbation, grows up, in fact, exponentially. And in that case, the system is unstable. So all existing nuclear power plants or reactors in operation have a negative feedback effect. So let me explain it in more detail. Suppose I have a perturbation where the temperature in the reactor increases. If the temperature in the reactor, in a light water reactor, the pressurized water reactor or the boiling water reactor increases, you'll find that the voids in the coolant increase. So in that case, the void increases, the number of molecules per unit volume or the density of the coolant decreases. As the density decreases, the moderation of the neutron decreases, less power is produced. Oh, you find that the temperature now that was increasing as a perturbation goes down. So the system becomes self-regulating. We call this negative feedback effect, negative feedback. All right, in a reactor of the Chernobyl design, the water acts as a poison. So if you get a perturbation in the temperature increases. You'll find that the void fraction increases. The density, again, decreases. But as the density decreases, the moderation increases because the water acts as a poison. It's almost like the control rods being withdrawn. So the power, instead of going down, goes up, and the temperature keeps increasing. And we call this a positive feedback effect. So reactors in the United States cannot be licensed unless they have basically a negative feedback effect for stability. The Russians thought that because they had so many pressure tubes in their design that only one of them could fail and they thought it was fail-safe, but in fact, it was not, as we'll see as we study the progression and the causes of the accident in general. At some point, the Chernobyl accident was considered, today, actually, the Chernobyl area is north of the Ukraine, which was one of the USSR states, the Union of Soviet Socialist Republics that has been dismantled. The Ukraine became independent, and of course, you hear about the Ukraine war. Chernobyl now is part of the Ukraine. It is considered as the worst accident in the history of nuclear power generation, even more serious than the Fukushima accident because of the death of people caused by the accident. It was an experiment, and it was caused ironically. Now, this is a very interesting thing, is that it was caused by an experiment. And the experiment was designed to check the safety equipment. They wanted to see if the steam generated, if they shut down the reactor, can drive a pump, and that pump would really pump water for an auxiliary cooling system of the reactor. Things, of course, went awry, and there was a fire in the graphite core moderator. It lasted for 10 days, and it's a similar situation as Windscale. Unfortunately, we hadn't learned from Windscale. The British and the Canadians have learned from that experience. They had 2 reactors, one designated as a steam generating heavy water reactor in the UK, steam generating heavy water reactor, that's in the UK. And in Canada, they have a reactor called the John T. Yee reactor. And both of these used heavy water, D2O, as a moderator, and they used light water, H2O, here H2O as a coolant, and heavy water as a moderator instead of graphite as a moderator. And those 2 reactors, one in Canada, one in the UK, have been retired because, again, of that positive power coefficient of reactivity. I doubt that there will be any more reactor built with that capability or that design feature in general. So let's look at the design of the reactor plant itself. This is from a report from the IAEA, and you could see here the core of the reactor, graphite, hundreds of tubes, as you could see here. Those tubes would have light water moving in them, and as the water heats up, it's taken to those long cylinder here, 1, 2, 3, 4. They're called drums, and those drums are very typical in coal-fired power plants. So you pump the mixture of water and steam to the drums there. The steam exits from the top of the drums and goes to in the tubes and goes to the turbine building, and the water settles at the bottom of the drum and is pumped back into the core. And you could see here they had very large pumps pumping the water out. That reactor was built, or that design in particular in the old USSR, was built with a dual purpose kind of a function. It did produce both electricity, but it also was meant to provide them with plutonium in the case they needed for nuclear war. The old USSR, and including the modern Commonwealth of Independent States, has a doctrine of using nuclear weapons in case their country is facing an existential threat. So in that case, they designed it in such a way that they can access the top of the core with a large refueling machine shown here. They do not have the same containment structure as we have in, like we devoted a whole chapter, the ice condenser, for instance, in existing PWR or BWR. They needed to access the core. Why? If you want to produce plutonium for weapons, you cannot use the plutonium that is used in nuclear reactors, because as you leave the uranium-238 there for a long time, you produce an isotope of plutonium, plutonium-240, It undergoes spontaneous fission. It's also a very powerful alpha emitter. You cannot make weapons from reactor-grade plutonium. If you want plutonium for weapons, you irradiate your uranium-238 for no more than 2 weeks. In that case, you do not form that plutonium-240. So they had access to it from the top. And it was a good design from that perspective. And they had a very, very kind of confidence in their design in that they suggested that if something goes wrong, it may happen in one of those tubes here containing the light water, and they could isolate it and everything would be fine in that case. The reactor was designed to have 1,000 megawatt electric power production. This is in the name, RBMK 1000. 1000 here stands for 1,000 megawatt electric. The thermal power was 3,140. This means that it had an efficiency, thermal efficiency of about 1/3, 31.4% in that case. The coolant inlet temperature was quite low, 270 degrees Celsius, and the saturated steam was only 284. If you want to compare that to light water reactors, the PWR and the BWR basically have exit temperatures in the range of 360 degrees Celsius. They're nowhere, even though they are using graphite as a moderator, nowhere close to the high temperature gas-cooled reactor, which can have an outlet temperature of the gas, helium in that case, of around 900 to 1,000 degrees Celsius in general. The initial fuel enrichment, low enrichment, 1.8% in uranium-235. So from that perspective, it was considered as a safe reactor. And this is now from another diagram that shows us more detail about the reactor. And here is the core of the reactor. This would be the pumps. This would be here the steam drums. No solid containment structure. And that was some kind of discussed as a lack of containment of radioactivity in general, or a flaw in the design. That was not the case. The real flaw in the design is here at the bottom of the core. You could see here, if you read the legend for 28 and 29, do you see 28 here? They call it accident confinement system release valve, and 29 accident confinement system condenser. So they had the condenser there right below the core. And that is a flaw in the design, because it seems that the core, as it melted, you had now corium material. And we devoted a whole chapter, like what happened in the SL1 reactor, the military reactor in the United States. If you have metal interacting with water, you get a chemical reaction that can be extremely violent in that case. So I surmise that the core melted, interacted with the water here under the core. Steam explosion took that lid there that I have shown you in the earlier diagram and threw it up in the air. Now, the graphite was seeing the air, heat was being generated from the fuel, the graphite caught fire, and they had basically a very serious situation where radioactivity was released from the reactor itself. Again, I show you here the flaw in the design. And in fact, this is a feature that should never, ever be built again if you design any kind of a power plant. Here is the core. And look here, this is all water. If you look here at the legend number 6 and study the design, you'll find again here, they call it the pressure suppression pool. And in boiling water reactors, we make sure that that pressure suppression pool does not lie under the core. And when we study later on the Fukushima accident, you'll find that for boiling water reactors, right under the core, where the control rods come in from the bottom, there is an area that we call the dry well. And from the name itself, dry means that it should remain dry. It seems that water leaked under one of the units, unit number 3 in the Fukushima accident. The core melted, according to TEPCO, the Tokyo Electric Power Company, and the corium material may have interacted with that water that had leaked into the dry well. That is not substantiated yet. It's a topic for research to suggests that indeed, when we come back to the Chernobyl, to the Fukushima accident, I'll come back to that argument. That black, those black dark lines here is what they consider being the confinement structure. And obviously, it was not sufficient to stop the release of radioactivity to the environment. I try to emphasize again that that was a bad part of the design. It was not like the PWR design where you get the boiling water. It was a boiling light water reactor. In fact, you take the boiling light water and takes the steam out of the core. They take the steam here from the steam drum, same design as coal power plants in general, and that's where it goes to the turbine. All right, so again here, the confinement system from different sources. You could see very clearly here that here is the reactor, they call it the reactor space. That's a drafting. The confinement system is what they show here in dark, as a dark line, but water right under the core. So the possibility and probability if the core melts in any way and interacts with the water for a very serious steam explosion. All right, so it was both a situation like the wind scale accident where the graphite caught fire by its being exposed to the air, as well as the melted core probably interacting with the water under the core. And this is another drawing from the Russian literature. You could see here, it's a maze in terms of the number of tubes embedded into the graphite. Again, it's a nightmare in terms of piping there and the plumbing. And they thought that, oh, maybe one tube will go bad, and then of course we can isolate it and everything will be fine. That wasn't the case. It was a case of complacency, like the Minsky moment that we mentioned earlier in the semester in general. I say here the boiling light water coolant pipes are surrounded by the graphite moderator. So the coolant and the moderator are separate. So that was a reactor with a positive power coefficient of reactivity. It's by definition an unstable system. All right, so they operated, though they didn't know that, again, they had confidence that any credible accident can happen in one of the tubes and they can isolate it in general. The reactor cooling system had two loops. The steam water mixture leaving the core is led to two steam drums. They're really long cylinders, as you've seen in the diagram, where the separated steam is fed into the turbines, and that's where the electricity is being produced. The graphite provides a major part of the moderation. It is not the water. So the water there is not for moderation. The water is simply for boiling. And if you boil that water, it is equivalent to withdrawing the control rods and give us that positive power coefficient of reactivity. So in that case, it's very important for us to understand that positive power coefficient of reactivity. The light water, I say here, acts primarily as a neutron absorber and does not provide significant moderation. This means that a void in the water coolant could actually reduce the neutron absorption characteristic and increase the fission reaction rate, hence increase the power level. An increase in reactor power increases the coolant boiling, which increases the steam void fraction, which in turn increases core reactivity and causes the power to rise even further. This is typical of a positive feedback control system, and positive feedback control systems that do not kind of attenuate or squelch the any perturbation are inherently unstable. Don't put any positive power, any positive feedback system in any kind of engineering design that you make. So this positive feedback mechanism characterizes unstable systems in general. In control theory, it's worthwhile for you to study a little bit on control theory. And the positive power coefficient or void coefficient of reactivity for the RBMK exists under most operating conditions and makes them particularly difficult to control, and particularly even more at low power levels. And that affects the what I'm going to tell you later, that they were really conducting an experiment at low power level. Here is another diagram for that MK design. Here are the pumps here. Here are the steam drums. Here is the core, and under the core you have that pressure suppression pool that is containing water in general. All right, so let us study a little more of the design. The control rods are inserted into the core from the top. That is in contrast to existing boiling water reactors. Even though it was a boiling light water reactor, the control rods came in from the top. You'll find that it was a well thought design, but except for the positive feedback coefficient of reactivity, they had an online refueling machine. Why an online refueling machine? Because they wanted to be able to not open up the lid from the top of a PWR or a BWR only every year or a year and a half to refuel the system. They wanted to be able to insert uranium-238 and irradiate it for 2 weeks and get plutonium-239 for weapons. And because if it lasts longer, it is contaminated with plutonium-240. I explained that to you. It had a gas-tight containment steel vessel. It had a concrete biological field and structure. They had steam drums for steam and water separation. They had steam lines to the turbines and refueling channels through the top plate. They had, of course, a reactor core, main coolant pumps, and return water from the steam drum. So it was a design that looked like a standard design. And my contention that it was a dual-purpose plant is shown here in the diagram. These are people, as you could see here, walking on top of the core while it is in operation. That would not happen in other designs of reactors. I have shown you a diagram of the refueling machine, so they could bring in fuel in, irradiate it, produce plutonium, extract it within 2 weeks. So it was a power-producing reactor, but also a plutonium producer. And that's why the Russians, when they invaded the Ukraine, maybe they had in the back of their mind occupying the area where the Chernobyl plant was, because in that case, the Ukrainians can go on and produce plutonium and face them in terms of nuclear armaments in general. So that was not mentioned in the open literature, but that is a fact in general. It has some very good safety feature. And again, you could think about that problem that, oh, you put in safety features and you become complacent that, oh, only one tube can fail. But in fact, more than that happened. The reactor were equipped with multiple safety features. It had what's called the limiting fault condition, a loss of coolant accident with break in the pipe work of 90 centimeters in diameter. This is the design feature that we implement in boiling water reactors and light water reactors. The reactor is able to operate basically with 2,000 metric tons of graphite moderator at a temperature of about 700 degrees Celsius. Even though the operational temperature was about 250 degrees, they can raise the temperature to 700, and the graphite can absorb that heat. You know, graphite has good thermal inertia. It can resist high temperatures. That's why we use it in high temperature gas-cooled reactors. But of course, if it is hot and exposed into the air, it acts like charcoal. Charcoal catches fire at high temperatures. The containment consists of several engineered safety features, a pressure suppression pool, and that's similar to the boiling water design, but it was situated beneath the structure. This was an unsatisfactory design choice, since in the event of core meltdown, the molten corium material would cause a steam explosion. And that's why we devoted the whole chapter to the steam explosions. They had an emergency core cooling system. It would come into operation if either coolant circuit is interrupted. They used the boron carbide. Boron, as you know, is a very strong absorber for neutrons. So we use it in the control rods, and they use boron carbide, BC4. And that, in that case, that boron carbide, because it's a carbide, can take very high temperatures. It absorbs neutrons and controls the rate of fission. They had 211 control rods, quite a few of them. A few short rods inserted upwards from the bottom of the core also provided more control of the bottom part of the core. The reactor core is lined by concrete lined cavity. It acts both as a biological radiation shield, and you could see in the picture those people walking on top of the reactor while it was operating. The reactor core is located, we mentioned that. The steam drum separator of the coolant are housed in their own concrete shields, and to protect the crews there or the operating personnel against the isotope nitrogen-16. The isotope nitrogen-16 is typical of boiling water reactors. When you have the water introduced into the boiling water reactor, you'll find that the oxygen in the water absorbs a neutron and produces that isotope nitrogen-16. So in that case, in boiling water reactors in the United States, the access to the turbine hall, because in that case, the steam going to the turbine contains that nitrogen-16 is high enough, the access to it is very, very limited. Even though when I took one of our classes, the 402 class, to visit one of the LaSalle plant here in Illinois, they allowed us in just to show us the reactor operating during operation. Nitrogen-16 is a strong gamma emitter, but it has a very, very short half-life. In a few minutes after you shut down the plant, its radioactivity has disappeared. And in fact, in operating boiling water reactors, I've shown it to a class when the Clinton plant west of us was being under construction. They take the steam in a steam pipe, and the steam pipe is 1 meter in diameter. It's huge steam pipe. They take it to the top of the reactor building, then they turn it all the way to the bottom of the reactor building, and then raise it up to give that nitrogen-16 some time to decay before it is being fed into the turbine in general. The reactor is surrounded by a biological shield that is a tank filled with water 16.6 meters in diameter. The biological shield and the core are closed from above and below by cylindrical covers filled with serpentine-shaped shielding material through which multiple communication and instrumentation pipes would go through. These parts of the reactor were displaced during the accident. They formed passages through which the contents of the core were released, and of course, radioactivity was released big time to the environment in the same way as what happened in the Sellafield or the Windscale accident that we designed earlier. The very hot graphite core, like in the Windscale accident, is prevented from oxidizing by inert gases. What do you choose as inert gases? Oh, you use helium and nitrogen on top of the core. So the core during operation does not get in touch with oxygen in the air. Nitrogen, of course, does not burn, and helium does not burn. Graphite possesses a peculiar property. It is subject under neutron irradiation to an energy accumulation in its lattice structure caused by atomic displacement through that phenomenon that we discussed for the Windscale accident, the Wigner effect. The Wigner effect under irradiation, graphite stores energy, and you have really to anneal it to return the displaced atoms in the graphite back to their location in the crystal. Otherwise, the energy is released in an uncontrollable way, and you can get a fire. So to avoid the occurrence of hot spots, the graphite needs to be annealed at regular intervals, same as Windscale. And such a phenomenon is thought to have caused the earlier graphite fire accident and the Windscale reactor in the UK. The accepted practice is to nuclearly heat the graphite to bring the graphite moderator up to a temperature where the displaced atoms, simply by the mobility by the heat are returned back to their the vacancies that they came in from, and you continue operating the reactor. In the Windscale accident, that nuclear heating, as we have studied it, came in. They did it too fast, and as they did it too fast, they caused the release actually of that energy and caused the fire to occur. This is an interesting diagram. If you study it in detail, this is the accident sequence that happened in the case of the Chernobyl accident, and that is a detail that showed up after the accident when it was analyzed. And you'll find that the vertical lines are at 10-second intervals. So you see here the accident occurred quite rapidly, and at 1:23:43 here on the diagram, if we can enlarge it, I think this is the actual sequence of the accident. You'll find that at 1:23 in the morning, so it was really what they call the graveyard shift, where the unexperienced operators are asked to run nuclear power plants. And in fact, they were running a safety kind of an experiment when they shouldn't have done that. You'll find that the power increased suddenly there when they reduce the power of the reactor to carry out the experiment. And we'll deal with this later on, but we have to mention here also that steam, if steam is gets in touch with graphite, an interesting reaction occurs. It produces what's called producer gas. At some point in history, the producer gas was used to light up the streets of London, and it is a mixture of carbon monoxide and hydrogen. And you can produce that producer gas by simply running steam, hot water in that case, steam on top of hot graphite. So with the fire and the water, it was not only the graphite catching fire, but there they are producing the hydrogen and carbon monoxide that are also explosive at high temperature. And the high temperature of the zircaloy cladding itself can interact with the steam. And the reaction with any metal of hot steam, as you all know, is this. Like if you bring in steam, H2O, on top of hot iron, you'll find that you oxidize the iron. You burn the iron, literally, it becomes iron oxide, and you release hydrogen. In the case of those reactors, they use zirconium as a alloy. So in that case, you burn the zirconium oxide, and you release hydrogen. So look at all the sources of hazards now if things are not occurring as expected or as designed. You have the CO plus H2, you have the H2 with the interaction of the steam with the cladding, and that interaction of steam with the cladding happened also in the Fukushima accident on a big scale because those boiling water reactors had a core that would spray water if the core is uncovered. So it is not mentioned in the open literature, but that's a flaw in existing boiling water reactors. If you have a very high temperature, you can use core spray, as it's called, but only at low temperature. At high temperature, you get that reaction where hydrogen is produced and released to the containment. And in fact, it seems that that's what they had in three of the 4 reactors at Fukushima. They had hydrogen being released. They couldn't diffuse it out of the containment, and then it is documented that we had hydrogen explosions in that case. The zircaloy pressure tubes adjacent to the hot graphite were cooled only as long as the water pressure within the tube is maintained. If you lose the water pressure, you can raise the temperature of the zircaloy to that of the graphite. And the positive void and power coefficients, this is really the design flaw in the design, resulting from a neutron population increase the water coolant if the water coolant is boiled off. So you boil the water off, the temperature increases, and you get a positive feedback effect, and that would be a loss of coolant accident. This is basically the parametric scales in that sequence of the accident. And you notice here in the diagram that the core basically separated. This would be the original core. It's separated into two cores as the operators reduce the power of the reactor to see whether they can use the steam to drive a turbine for cooling the water. Very quickly here in the time that we have left here, you'll find that the operator started to reduce the power on April 26, 1986 to 720 megawatt thermal and continued to be reduced. They didn't know that at low power, the reactor has a positive power coefficient of reactivity. They didn't want to shut down the reactor for a long time. They needed power for the city of Kiev, which is the capital of the Ukraine. So they kept bringing the power down, and at that point, the reactor became very much more unstable. And they even disconnected the automatic control system that was trying to shut down the system. And suddenly, within microseconds, the power really increased to about 20,000 megawatt thermal. The operator heard the alarm. They went there and pushed the scram button. The scram means shut down the reactor. That was too late, and the rest of it is history. So what is the situation today with ignoring the warnings? This is what we have now, a reactor that's totally destroyed, highly radioactive, and it has been enclosed in what you could see here, a large concrete silo. Originally, that's what they built. And then they brought in a steel structure on top of it. Reactivity was released in the same way as the Sellafield or the Windscale accident to Europe. This is a picture now on the interior of the reactor, totally destroys, trying to remove stuff that and decrease the contamination. This is now how the control room looks like, totally devastated. The area around the plant has been at a city called Pripyat, has been basically left out. And this is Kiev, the capital of the Ukraine. This is the location of the Chernobyl nuclear power plant. The main radioactivity that was released, let me just finish that very quickly, is cesium-137. And we know that it decays quite rapidly. So we are at a range now where the decay has gone down, and nature is taking over. That's the cesium levels in 2014. And they brought in fact, a large steel structure on top of the reactor. And now it is isolated from the environment. And I show you here the table, the scale rating of some nuclear incident. The 3 Mile Island is rated as INS. INS stands for the level of the seriousness of the accident. 3 Mile Island is a level 5, as we'll study later. Windscale, also a level 5 accident. And let us see here very quickly how the Chernobyl is level 7, as well as Fukushima. So both Chernobyl and Fukushima as rated as level 5 accidents in the nuclear industry. This is the way it looks like right now. The 3 other reactors have not been affected. They continued producing power. I am not sure that they, and this is the latest picture of that unit number 4. Unit number 3 is right there. They can continue operating it if they wish. This is the way the reactor basically is isolated over time. And these are the people who worked on it. It was heroic of the people, the firefighters, that tried to extinguish the accident. They were subjected to radiation. They knew that they could be killed, and 31 of them were lost to the accident. So I would like you to read the rest of the material that we cannot cover during a single lecture. And please to identify the following causes of accidents in general in the nuclear field. It could be design flaws. We identified some design flaws. It could be human error when they overcame the automatic control system. And I have to quote here one Russian scientist, and then I'll close I'll close the lecture. The violations in that case of the safety rule, the human errors, was, according to a Russian scientist, it was like airplane pilots experimenting with the engines in flight. And the test was conducted by an electrical engineer who obviously did not know the physics of the reactor that he was responsible for, so that one can extend the analogy to, it was like a passenger airplane pilot experimenting with the engine of a fighter jet in flight. The most disturbing aspect of the Chernobyl accident has to do with the side effect of the use of complex systems. So we can go back to the chapter that earlier in the semester about complex systems by uninformed individuals. Individuals that use complex systems should be well informed, otherwise the whole of humanity suffers from it. And thank you for sharing with us. Thank you, Anshal, and we